Welcome to HFCL Time Machine. Past, present, future, all connected.
Let's step into today's chapter, where we explore how mobile data offloading is helping telecom operators unlock more capacity from existing networks and what it means for the future of seamless connectivity, spectrum efficiency, and the ever-growing demand for mobile data. And, if you are joining us for this deep dive, I already know a bit about you. You are the learner.
Right, exactly.
You are that person who doesn't just want to blindly trust that your phone will work, right? Like when you are trying to stream a cricket match on a crowded train, you want to actually know how it is pulling that off.
Yeah, you want to look behind the curtain.
Exactly. And today's mission is exactly that. We have a solid stack of sources on the table today, industry reports from Ericsson, market projections, and some pretty heavy technical architecture documents from HFCL.
Very heavy, actually, but fascinating.
Right. So we're going to figure out how these networks haven't completely collapsed under the sheer massive weight of our daily data habits.
Because honestly, when you look at the raw physics of telecommunications, it is genuinely a modern miracle that they haven't collapsed. I mean, TSPs, or telecom service providers, are basically executing this constant high-stakes balancing act every single second, right under our noses.
Absolutely. And to really set the stage for you, the listener, we have to talk about the sheer scale of this.
Yeah.
The numbers we're looking at are just staggering.
They really are, especially if you look at India.
Yes, let's take India as the prime example here. In 2023, India had the world's second largest internet user base. We are talking about over 1.2 billion people in total.
Right, and out of that, a massive 1.05 billion were accessing the internet primarily via their mobile phones.
It's just wild. And the projections, they expect this mobile internet user base to cross 1.2 billion by the year 2050. I mean, it's practically an ocean of smartphones out there.
It is an ocean, absolutely.
Right.
But here's the thing. What keeps telecom network engineers awake at night isn't just the sheer number of people buying devices.
Really? What is it then?
It is the actual volume of data each of those individuals is consuming. See, adding more users to a network is a fairly predictable challenge, but a user base whose data appetite is doubling, tripling, just multiplying year on year.
Right, that just throws all the math out the window.
Exactly. It fundamentally breaks traditional network architecture.
I mean, think about it. We aren't just sending, text messages anymore. We are streaming 4K video. We are on constant video calls. We are gaming.
Yeah, we are basically in the middle of this invisible data tsunami.
Totally. And to put a number on the weight of this problem, let's look at the global surge from our Ericsson reports. Back in 2018, the total global mobile data traffic was sitting at around 19.01 exabytes per month.
And just for context, 1 exabyte is a billion gigabytes.
A billion gigabytes,
Yeah.
right. Then you fast forward to 2022, and that number just rocketed to 77.5 exabytes per month.
And we can actually drill that down to the individual level, a device you're holding right now. Global average data usage for a single smartphone jumped from about 15.93 gigabytes a month in 2022. Let me guess, it doubled.
More than that, it jumped to an expected 56 gigabytes by the end of 2023.
Oh, wow. Which brings us right back to India, actually, because according to the data, this is where the absolute extreme edge of this trend lives.
Absolutely. India boasts the highest average data traffic per smartphone anywhere in the world.
Yeah, we are looking at a jump from 31 gigabytes per month in 2023 to a projected 75 gigabytes per month by 2029.
75 gigabytes every single month per user.
Okay, let's unpack this. Let's say we think of licensed spectrum, the actual cellular radio frequencies that telecom providers buy from the government as this highly exclusive VIP toll highway.
That's a good way to look at it.
Right. So if that highway is completely gridlocked with all these 75 gigabyte a month cars, why can't the telecom providers just buy more land and build more lanes? I mean, why not just put up more cell towers everywhere?
This raises an important question, and honestly, it is usually the first logical jump people make.
Right. Just build more towers. Yeah, but the answer comes down to the unforgiving limits of physics and then, well, economics. See, licensed spectrum is strictly finite. It is a very specific, narrow band of radio frequencies.
So you literally can't manufacture more of it.
Exactly. You can't just make more. Because governments auction this off and it's so incredibly scarce, it is astronomically expensive. TSPs are spending thousands of crores just for the right to transmit data on these specific waves.
Right, okay, but what about the towers themselves? If they have the spectrum, why not just saturate the city with Enode bees? those 4G base stations?
Mainly because of how radio waves work in dense physical spaces. If you just brute force it and put massive cell towers on every single building in a dense urban environment like, say, Koramangala or Lower Peril, their signals start crashing into each other.
Oh, so you get massive interference.
Exactly. Plus, the logistics are a total nightmare. Securing the real estate for heavy tower equipment, establishing the fiber backhaul to connect them all, securing reliable power around the clock.
I can imagine the costs just spiraling out of control.
Completely. The capital expenditure to acquire the spectrum and build that heavy physical infrastructure would completely bankrupt the providers, or, they'd have to pass the cost on to you, and your monthly mobile bill would skyrocket.
Nobody wants that.
Yeah.
So expanding the VIP highway is effectively impossible. You can't pave over the whole city, and you can't defy the laws of radio interference.
Precisely.
But people are still demanding their 75 gigabytes. If the highway is full and you can't build more lanes, you naturally have to redirect the traffic to the side streets.
Right. And in the telecom world, those side streets are the unlicensed spectrums.
Ah, and this is exactly the strategic detour we call mobile data offloading, or MDO.
Yes, MDO. It is basically the only viable escape valve telecom operators have right now.
Okay, so break that down for me. What exactly is MDO doing?
So MDO is the process of taking that heavy gridlocked data traffic off the expensive licensed cellular spectrum and redirecting it onto available unlicensed spectrums, which in most cases means Wi-Fi networks.
And the absolute magic word here when we talk about unlicensed spectrum is that it is free.
Right.
The government isn't auctioning off Wi-Fi bands.
Exactly. Anyone can use them.
Right.
Which creates what the industry sources refer to as a threefold savings reality for the TSPs.
Okay, threefold. What are we looking at?
Number one, you dodge those astronomical spectrum auction costs we just talked about. Number two, you slash your deployment costs.
Wait, let me stop you there and push back on that a bit. Slashing deployment costs.
Yeah, significantly.
But if a telecom company has to go out and deploy hundreds of thousands of Wi-Fi access points across a city to offload this traffic, that sounds like a massive infrastructure nightmare of its own.
I see where you are going.
Right, like how on earth is buying and installing 1 million Wi-Fi routers cheaper than just upgrading a few hundred existing cell towers?
It is a totally valid question, but you have to look at the form factor and the power requirements. Upgrading or deploying a 4G base station, a macro cell tower, requires heavy structural engineering.
Sure, huge steel towers.
Right. Huge power draws, massive cooling systems, and specialized maintenance crews. A commercial Wi-Fi access point, on the other hand, is tiny. It uses standard power.
Oh, so you can just bolt it to a lamppost or something.
Exactly. A lamppost, a ceiling inside a mall, or an existing utility pole. Setting up a highly capable Wi-Fi hotspot costs a mere fraction of what it takes to deploy a 4G base station.
That makes a lot of sense. It is significantly cheaper than even deploying smaller cellular nodes like femtocells.
Much cheaper. The hardware itself is lighter and way cheaper to scale.
Okay, fair enough. And I'm guessing the third part of those savings is that customer complaints drop because the network isn't constantly buffering.
You've got it. It is a brilliant pressure relief valve.
So everyone wins.
Pretty much. When you siphon off that heavy data congestion, the remaining users who have to stay on the cellular network suddenly get a much faster, cleaner experience. Meanwhile, the users who are offloaded to Wi-Fi get high-speed local data.
Here's where it gets really interesting, because I am putting myself in the shoes of the listener right now.
Okay, let's hear it.
Picture this. You are walking down a busy street in a tech park. Right. You are on an important video call.
Sounds stressful already.
Exactly. Now, historically, when we think about using public Wi-Fi, it is a mess. We think of having to stop walking, open our settings, search for a network.
Right. Maybe find one called Cafe Guest, click it.
Yes. Then wait for an annoying web portal to pop up, type in an OTP. It is a completely clunky process.
It is.
So how did telecom operators actually move my massive data stream over to these Wi-Fi side streets without me dropping my video call or even noticing a lag?
That is the most crucial distinction we have to make today, because what you are describing is consumer Wi-Fi.
Right.
Modern carrier-grade mobile data offloading is absolutely nothing like that. It is an intelligent, completely invisible redistribution of traffic.
Invisible, you say?
Completely. It all happens through a mechanism called EAP SIM authentication.
Okay, you need to make sense of this EAP, Stormy. What is actually happening in my phone?
So, when your phone detects a carrier-managed Wi-Fi access point, you don't get a splash page. Instead, The network infrastructure and your device's SIM card have a high-speed cryptographic conversation in the background.
Over the Wi-Fi radio waves.
Yes, exactly. The mobile core essentially says, I recognize the encrypted credentials on this physical SIM card. This is a paying customer. Let them in.
And this happens instantly.
In milliseconds. When the system detects that the cellular tower is choking and it sees a robust Wi-Fi access point nearby, it authenticates your SIM securely and seamlessly hands over your data session.
And I don't have to lift a finger.
You don't lift a finger. You don't enter a single password.
That is wild. The network just dynamically shifts the weight around based on cryptographic trust, which I guess brings us to the actual technology executing this.
Right, the brains of the operation.
Because theorizing about moving traffic is easy, but engineering the hardware and software to execute this invisible handoff millions of times a second without dropping a single packet.
That is incredibly hard.
Yeah. And in our sources, we are looking specifically at how HFCL's access solutions are tackling this huge architectural headache.
Yes. What HFCL has done is engineer a very comprehensive end-to-end MDO solution specifically tailored for these telecom service providers.
And their entire philosophy here is seamless integration, isn't it?
Exactly. Their system is designed to plug directly into the various industry-standard mobile cores that operators already run.
So they aren't going to Vodafone or Geo and saying, hey, rip out your entire legacy foundation to install our stuff.
No, not at all. They're building a highly intelligent layer that sits right on top of it.
That's brilliant. And from the architecture documents we reviewed, the central brain of this whole operation is something called the Cloud Network Management System, or CNMS.
Yes, the CNMS.
But tell me something. Telecom companies have been managing their networks for decades. Why is this CNMS suddenly the big game changer?
Because the legacy way of managing these offload networks was entirely fragmented.
Fragmented how?
Well, in the old days, telecom operators had to use separate hardware-based network controllers just to keep the Wi-Fi points running, and then a totally separate element management system, or EMS, to monitor alarms and performance.
Sounds completely disjointed.
It was. What the CNMS does is unify all of that into one centralized, cloud-based platform. It gives the providers complete control from a single pane of glass.
So they can just manage everything from one dashboard.
Exactly. They can push bulk firmware upgrades to 100,000 access points at once, streamline their configurations, and run advanced diagnostics.
And reading through the specs, what really caught my eye was the integration of AI within this CNMS.
Ah, yes. The AI is a massive leap forward.
Right, because we aren't just talking about a dashboard that blinks red when a router dies. The AI is doing remote monitoring and predictive troubleshooting, right?
Correct. The AI in the CNMS analyzes traffic patterns and hardware telemetry to actually predict and troubleshoot network bottlenecks before they cause a total outage.
Which I imagine drastically cuts down on their physical maintenance costs.
Oh, massively. You don't have to send a truck roll, a technician in a van to figure out why a node is acting up if the AI can reconfigure it remotely.
Okay, so that's the cloud brain. But then you have the actual physical hardware bolted to the walls, transmitting the signal, the access points themselves.
Yes, the APs. And HFCL's suite includes both indoor and outdoor access points.
And they use Wi-Fi 5 and 6, right?
Yes, they utilize Wi-Fi 5 and the newer, highly efficient Wi-Fi 6 standards, which are specifically designed to handle dense environments with hundreds of devices.
But what is truly vital here is that these access points are vendor agnostic.
Which is a huge selling point.
Right, which means they play nicely with whatever massive global network infrastructure a telecom provider might already be using. They aren't trapping the TSPs inside a proprietary walled garden.
Exactly. Now, because they are managed by that central CNMS brain, the operator has total control. But the access points themselves are incredibly intelligent at the edge.
What do you mean by intelligent at the edge?
Well, they have built-in functionalities that are absolute requirements for this invisible handoff to actually work in real life. We are talking about features like ATPC, load balancing, band steering, and ACS.
Okay, I'm going to have to jump in right here because we just threw a very dense alphabet soup of technical jargon at the listener.
Fair enough, I get a bit carried away.
Let's slow down and translate these smart functionalities. Explain how they actually control the chaos. Let's start with ATPC.
All right, let's break down the mechanics. ATPC stands for Automatic Transmit Power Control.
And what does that actually do?
See, if you have 10 Wi-Fi access points in a stadium and they're all blasting their radio signal at maximum power, they will cause massive interference with each other.
Oh, sure, just creating static.
Right. So ATPC allows the access point to intelligently scale its signal strength up or down in real time, matching exactly what the connected devices need and minimizing noise in the air.
Oh, I get it. Like people in a crowded room learning to whisper to the person next to them instead of everyone shouting at the top of their lungs.
That is a perfect way to put it.
Makes sense. What about load balancing?
Load balancing ensures that if 100 people suddenly walk into the range of access point A, it doesn't just crash under the weight, especially if access point B, 20 feet away, is sitting totally idle.
So it just shuffles the users around.
It actively redistributes those users across the available hardware, yeah.
But what's really fascinating here is band steering.
Right, because modern Wi-Fi routers broadcast on two different frequencies, typically 2.4 gigahertz and 5 gigahertz. How does band steering manage that?
So the 2.4 gigahertz band is slower, but it travels further, and a lot of older devices or smartwatches use it. The 5 gigahertz band is incredibly fast, but it has a much shorter range.
Okay.
Band steering actively identifies modern, capable smartphones and forcefully steers them onto the faster 5 gigahertz frequency.
Which clears out the congestion on the 2.4 band for the older devices that actually need it.
Exactly. It optimizes the airspace for everyone. Okay. And the last one, ACS, automatic channel selection.
ACS acts as a constant environmental radar. You have to remember, unlicensed spectrum is shared airspace.
Right. Anyone can use it.
Meaning a nearby microwave oven or a sudden burst of Bluetooth devices can cause sudden interference on a specific Wi-Fi channel.
Oh, a microwave can actually mess with Wi-Fi.
Oh, absolutely. So ACS constantly scans the airwaves, and if it detects noise on, say, channel 6, it dynamically shifts the network to channel 11 in milliseconds.
Without the users ever noticing a drop.
Exactly.
It is literally an incredibly smart air traffic controller. I'm picturing an airport where the controller isn't just telling planes where to land.
Right.
They are instantly, dynamically rerouting planes to the absolute best available runways in milliseconds, actively adjusting their speeds, grouping faster jets away from slow propeller planes.
And ensuring absolutely nobody has to circle in the air waiting for permission to land.
Exactly.
That is a brilliant analogy. If we connect this to the bigger picture, all these edge features, ATPC, band steering, ACS, they synergize to optimize the unlicensed spectrum automatically.
It really is a highly space-efficient and power-efficient strategy.
Completely. The key takeaway is that telecom providers aren't just blindly dumping their excess traffic onto a cheap Wi-Fi network and crossing their fingers. They are actively architecting and managing that unlicensed spectrum.
Ensuring it performs at a standard that is just as good, if not far better, than the cellular network it is relieving.
Spot on.
So we've got the massive problem of the data tsunami. We have the strategic detour of offloading to unlicensed Wi-Fi side streets. And we have this brilliant HFCL technology acting as the air traffic controller via CNMS.
It is a solid foundation.
But does it actually work in the wild? I mean, is this just a good theory, or are we seeing actual proof? Let's talk about the real-world impact and the scale of this solution based on our sources.
Well, the results in the data we reviewed are quite profound, actually. In the zones where this specific mobile data offloading solution has been deployed, a massive 65% of overall data traffic is successfully offloaded to Wi-Fi.
Wait, let that sink in for a second. 65%.
65%.
That is taking 2/3 of the heavy trucks off that congested VIP cellular highway and effortlessly shifting them onto high-speed side streets.
Yes. The relief on the licensed cellular spectrum must be, well, it is immense.
It has to be.
And looking at the sheer scale, specifically in India, HFCL's deployed MDO solutions are currently serving between 5 to 6 million unique mobile users every single day.
5 to 6 million people daily. And the craziest part is, because of that EAP SIM authentication we talked about, those 5 million people probably have absolutely no idea.
None at all.
Their phones are dynamically hopping between cellular and Wi-Fi networks just to keep their Instagram reels playing or their Zoom calls connected.
And that is the ultimate mark of truly successful infrastructure. It is entirely invisible to the end user.
That's true.
And the deployment of this technology creates this beautiful dual benefit for the ecosystem. On one side, the telecom service providers are experiencing substantial revenue growth and margin protection.
Why? Because of those massive savings in spectrum acquisition costs?
Exactly. That and traditional 4G physical deployment expenses. Their operational overhead drops significantly.
While on the other side of the equation, the users are getting accelerated data consumption and completely decongested cellular networks when they actually need them.
It really is a win-win. We actually have a great perspective on this from the sources.
Oh, right. Shashank Sejwal, who's an assistant general manager at HFCL, weighed in on this.
Yes, he highlighted how proud the team is of these game-changing strides in MDO.
But what stood out to me wasn't just the technical boast. He specifically pointed out a shift in philosophy. Their focus is purely on innovative, customer-centric solutions.
Right. They are empowering these massive telecom providers with cost-effective, seamlessly integrated applications.
And the ultimate goal, as he notes, is scaling these specific achievements globally to reshape telecom networks worldwide.
They really want to drive down those operational costs while vastly improving what you, the user, actually experience on your screen.
It's a very pragmatic, necessary approach, don't you think?
Oh, absolutely. They recognized early on that supplementing existing macro networks with complementary technologies like Wi-Fi isn't just a neat parlor trick anymore.
Right, it's a necessity.
It is an absolute foundational necessity in this evolving paradigm of global telecommunications. You basically cannot survive as a TSP today without a massive offload strategy.
So what does this all mean? Well, to you, the learner listening to this deep dive right now, perhaps you are commuting through a dense urban grid.
Or maybe you were standing in a packed stadium with thousands of other people.
Right, all of you trying to upload a video to social media at the exact same time.
Yeah.
This invisible technology, this intelligent dance between licensed and unlicensed spectrum, is the very reason you aren't staring at an endless spinning buffering wheel.
It is a brilliant, silent bridge.
Exactly.
Yeah.
Built between our soaring, insatiable 75 gigabyte demands for data and the very real, finite physical limits of the radio spectrum around us.
It really is the invisible architecture of our modern digital lives. But, as we look at those Ericsson projections, remember, 75 gigabytes per month per user in India by 2029.
Yeah, that number's still wild to me.
It leaves me pondering the next technological horizon. We are already successfully shifting 65% of traffic in these MDO zones to unlicensed Wi-Fi spectrums today.
Okay, where are you going with this?
Well, what happens when our collective data appetites grow so exceptionally large that even the unlicensed side streets become entirely gridlocked?
Oh,
Will the future of telecommunications require a complete paradigm shift, where our actual smartphones have to act as mini towers, dynamically offloading, meshing, and relaying data for each other just to keep the global flow of information moving?
and that brings us to the end of this chapter in the HFCL Time Machine. Until next time, stay connected to what's next.
You've been listening to HFCL Time Machine. For more conversations like this, find us on LinkedIn, Instagram, and YouTube.